The night sky had always seemed eternal. For centuries, humanity lifted its gaze to the heavens and believed it was looking upon the totality of creation. Stars scattered across a dome, faint clouds of light stretching like pale rivers. To the naked eye, there was no sense of distance, no depth. Only a canopy of brilliance, close, familiar, and contained. Through ancient telescopes, faint smudges appeared. They were catalogued in silence, noted as nebulae. To astronomers of the 18th and 19th centuries, these spirals and ellipses were thought to be clouds of gas drifting within the Milky Way, mere ornaments in the grand expanse of our home galaxy. The universe, they believed, was singular, and we lived within it entirely. But in the early years of the 20th century, that fragile assumption was shattered. It was Edwin Hubble, working from the clear, dry skies of Mount Wilson in California, who first pried open the veil of ignorance. With the 100-inch Hooker telescope, then the most powerful eye humanity had ever built, Hubble studied a faint spiral smudge in the constellation Andromeda. Within that smudge, he detected a pulsing star, a Cepheid variable. These stars, with their predictable rhythm of brightening and dimming, serve as cosmic yardsticks, their luminosity tied to their distance. What Hubble uncovered was staggering. The Cepheid star in Andromeda was far beyond the edge of the Milky Way. This spiral nebula was not a cloud within our galaxy. It was itself a galaxy, a vast island of hundreds of billions of stars, separated from us by 2.5 million light-years of emptiness. With this realization, the known universe exploded outward. Those delicate smudges that had once seemed decorative were suddenly revealed as galaxies, each one a colossal structure, each one a universe of its own. The shock reverberated through science and philosophy alike. Overnight, humanity's place in the cosmos shrank to near insignificance. The Milky Way was no longer the whole, but just one island in an ocean of countless others. For every star above, there were billions unseen, stretching outward into depths beyond imagination. Astronomers began to call them what they were: island universes, great cities of stars floating in a dark sea. Each spiral, each elliptical glow, a cosmic metropolis of suns, planets, and perhaps the seeds of life. But with revelation came a new puzzle. If galaxies exist, if these immense structures populate the cosmos in staggering number, how did they come to be? The question lingered like a haunting echo, for even in the 1920s, the very idea of their existence posed a challenge. Galaxies were not small. They were not ephemeral clouds. They were grand, structured entities, billions of stars cohering into vast gravitational dances. And yet, the laws of physics suggested that building something so immense would take extraordinary amounts of time. Far more time than the universe was then believed to have. This paradox hung over the new field of extragalactic astronomy. On one hand, the evidence was undeniable: galaxies existed. They filled the night sky in uncountable number. On the other, their very presence seemed impossible. How could such sprawling complexity have arisen in the short cosmic history that physicists imagined at the time? Still, the discovery was a threshold moment. Humanity had crossed from myth into scale. The stars above were no longer points on a celestial dome. They were part of a deeper, more intricate architecture. In the years that followed, telescopes turned outward, cataloging more and more galaxies. Astronomers counted spirals, ellipticals, irregular swirls of light. They began to see filaments and clusters, galaxies drawn together by invisible bonds. The universe itself seemed to arrange into a cosmic web, each galaxy a node in a vast unseen network. Yet beneath this cartography, the mystery of their origin remained unsolved. The universe had revealed its immensity, but not its mechanism. And so the discovery of galaxies was both an expansion and a riddle. Humanity had learned that it was small, inhabiting but one star among billions, in a galaxy among billions more. But it had also inherited a deeper question. If galaxies are the architecture of the cosmos, what hands or what forces laid their foundations? The answer would not be found easily, for it required peering deeper into time itself, back to an age before stars, before galaxies, before structure of any kind. An age when the universe was young, and its future, the very possibility of galaxies, still uncertain. It is here, in this paradox of revelation and ignorance, that the story of galaxies truly begins. For in discovering them, humanity had touched the edge of infinity. And with trembling hands, it began to ask, not only what is out there, but how did it come to be? In the beginning, there were no galaxies, no stars burned, no planets circled in darkness. The universe, newly born, was a blinding ocean of heat. Energy surged in every direction, trapped in a plasma of particles so dense, so tightly bound together, that light itself could not move freely. For nearly 400,000 years after the Big Bang, the cosmos was a furnace of chaos. Electrons and protons collided endlessly, unable to form stable atoms. Photons, particles of light, were scattered at every turn, unable to escape the crowded soup. The universe glowed, but its glow could not travel. It was as if existence itself had been wrapped in an opaque fog, a veil drawn across the newborn cosmos. Then, slowly, the fire began to cool. As the universe expanded, its temperature dropped. Matter lost some of its violent energy. At last, protons and electrons found a moment of stillness long enough to bind together, forming the first atoms of hydrogen and helium. In that instant, the fog lifted. Photons, no longer trapped, began to travel freely through space. Astronomers call this moment recombination, the cosmic dawn when the universe first became transparent. It is this light, stretched by billions of years of expansion, that still travels to us today, the faint, frozen echo of a moment nearly 13.8 billion years ago. In 1965, Arno Penzias and Robert Wilson stumbled upon this ancient glow while tuning a radio antenna in New Jersey. At first, they thought it was noise, perhaps interference, perhaps the faint hum of pigeons nesting in the telescope's receiver. But the signal persisted. It came from every direction, uniform and unrelenting. What they had discovered was not noise, but history itself, the cosmic microwave background, the fossil radiation of the infant universe. This faint microwave signal, only a few degrees above absolute zero, became one of the most profound discoveries in all of science. For in its delicate pattern lay the fingerprints of creation. To the human eye, the CMB is a smooth, featureless glow. But with sensitive instruments, satellites like COBE, WMAP, and Planck, astronomers uncovered its hidden texture. Tiny fluctuations, differences in temperature no greater than 1 part in 100,000, ripple across this ancient light. These fluctuations are not random. They are the seeds of all structures. They are wrinkles in the fabric of spacetime itself, tiny pockets where gravity pulled just a little harder, where matter gathered more thickly than in the void around it. Over billions of years, these slight variations grew into great rivers and clumps of matter, collapsing into stars, merging into galaxies. Every spiral in the night sky, every glowing cluster of galaxies, every world, even our own Earth, traces its origin back to these delicate scars imprinted on the cosmic background. It is a humbling thought. The grandeur of galaxies, the architecture of the universe, all began as the faintest whispers of imperfection. Without those wrinkles, the universe would have remained a uniform fog, evenly spread, silent and sterile. Instead, from those subtle asymmetries, gravity sculpted the great tapestry of existence. Cosmologists often describe these fluctuations as quantum in origin. Tiny fluctuations in the earliest moments, amplified during the period of cosmic inflation, when the universe expanded faster than light itself, were stretched across the cosmos. What began as quantum uncertainty on the smallest scales became written across the sky as the blueprint of galaxies. Here lies the paradoxical beauty of creation. The immeasurable vastness of galaxies may owe their birth to the trembling uncertainty of the quantum world. The CMB is more than an echo. It is a map, a chart of the universe as it once was, and a prophecy of what it would become. By studying its ripples, astronomers have measured the age of the cosmos, its shape, its contents. They have seen in its geometry the presence of dark matter and dark energy, forces invisible yet dominant. But above all, the CMB speaks of beginnings. It tells us that galaxies were not conjured whole, but patiently built upon faint foundations laid in the first breath of time. Even now, satellites like Planck have revealed the astonishing detail of this pattern. We see not only the seeds of galaxies, but the subtle harmony of sound waves, pressure ripples that once echoed through the hot plasma, leaving their mark on the CMB like the aftertones of a cosmic symphony. These baryon acoustic oscillations, frozen in place, remind us that the universe itself once rang with a kind of music. A music that seeded the galaxies to come. And yet, a haunting limitation remains. The CMB is the furthest light we can see. Beyond it, the universe was opaque. The time before recombination, the first 400,000 years, remains hidden behind that curtain of fire. We cannot look directly upon the very first instance when the seeds of galaxies were sown. We can only infer, through theory and indirect evidence, what may have unfolded. Some scientists dream that one day gravitational waves, ripples in space-time itself, may offer us a way through that veil, carrying echoes from the universe's first heartbeat. If detected, they might reveal the very birth of those first quantum fluctuations, the sparks from which galaxies ignited. Until then, we look to the CMB as our earliest witness. A faint, ancient glow stretched across the heavens, whispering of a time when there were no galaxies, only potential. Every spiral arm of stars, every luminous cluster, every wandering planet traces its lineage back to this fragile moment, to those tiny imperfections that dared to exist in a universe that might otherwise have been featureless. From the smallest of ripples came the largest of wonders. From the first seeds of light, galaxies were destined to be born. The universe revealed its grandeur earlier than expected. In the deepest fields of vision, where telescopes stared into the silence of time, galaxies appeared. Spirals, ellipticals, and strange irregular swarms of stars glowed in the infancy of the cosmos, less than 1 billion years after the Big Bang. Their presence was a revelation, but also a contradiction. For by the rules of physics as they were once understood, galaxies should not have been there at all. The young universe was expanding too quickly. Gravity, though universal, was thought to be too feeble to gather matter into vast structures in such a short span. The smooth glow of the cosmic microwave background revealed a cosmos of near-perfect uniformity. Tiny fluctuations of density, yes, but scarcely more than a whisper of contrast. How could such faint ripples in matter, spread across a rapidly stretching space, give rise so swiftly to galaxies of immense mass and complexity? The problem was not only scale, it was time. If the Big Bang marked the beginning 13.8 billion years ago, then galaxies observed at high redshift, their light stretched by the expansion of space itself, were shining less than 1 billion years into cosmic history. Yet many of them already appeared mature, laden with billions of stars, and in some cases, even hosting central black holes of inconceivable mass. The question resounded through the halls of science. How had the universe built so much, so soon? This was the first great shock of galactic cosmology. Early theories imagined a slower unfolding. Matter would gather, slowly and gently, coalescing into small clumps, which in time might merge into the great galaxies we see today. But the data painted another picture. Galaxies were there, early and everywhere, luminous beacons far too advanced for the laws of growth as they were then known. It was as though the cosmos had leapt ahead of schedule. Scientists searched for an explanation, and in that search emerged one of the most profound ideas in modern physics: dark matter. Invisible, intangible, and silent, dark matter does not interact with light, cannot be seen directly, yet its gravitational presence exerts a profound influence. Astronomers proposed that the ordinary matter we know, protons, neutrons, atoms, gas, dust, was only a fraction of reality. The rest was hidden in this dark substance. Unlike ordinary matter, which was slowed and scattered by radiation in the early universe, dark matter was free to collapse. Its invisible gravity could begin sculpting structures even before atoms had fully formed. It became the scaffolding of the cosmos. In this model, galaxies grew where dark matter halos gathered, pulling ordinary gas into their invisible wells. The stars we see today formed in the gravitational cradles of what cannot be seen. This idea offered a solution but also a paradox of its own. For dark matter remains elusive. Despite decades of searching, no detector has captured its particles. No collider has revealed its substance. It is inferred only through its effect: the rotation of galaxies, the bending of light, the growth of structure. Without it, galaxies should not exist. With it, they are inevitable. The shock deepened as instruments grew sharper. With the Hubble Space Telescope, astronomers probed ever farther, revealing galaxies at redshifts of 10 and beyond, their light traveling for more than 13 billion years. These galaxies were not dim wisps, barely holding together. They were vast, bright, and in some cases surprisingly ordered. And then came the James Webb Space Telescope. Its infrared eyes pierced deeper still, uncovering galaxies so massive, so luminous, in epochs so early, that even the scaffolding of dark matter seemed stretched to its limit. In the first few 100 million years of existence, the universe was already assembling structures larger and older than models had predicted. Galaxies, it seemed, were forming faster than even dark matter allowed. Here lies the heart of scientific shock. The universe, governed by known laws, should have been too young, too smooth, too restless to build the grand cities of stars so quickly. Yet there they were, scattered across the cosmic dawn. It is a contradiction that unsettles the foundations of cosmology. Perhaps our understanding of gravity itself is incomplete. Perhaps the properties of dark matter are stranger than imagined. Or perhaps there are other forces at play, still hidden in the fabric of spacetime, guiding the universe toward complexity at a pace we cannot yet explain. What makes this paradox profound is not only its challenge to theory, but its scale of implication. If galaxies truly should not exist, and yet do, then something fundamental in the blueprint of the cosmos remains missing from human knowledge. It is as though the universe holds a secret, concealed within its very architecture, whispering through the contradiction between what we predict and what we observe. This tension is not merely mathematical. It is existential. For in the heart of the paradox lies a mirror to our own presence. Without galaxies, there would be no stars. Without stars, no planets. Without planets, no life to wonder at the night sky. The very fact of our existence is bound to this impossible truth. The universe built galaxies when it should not have been able to. Science advances by such shocks. When reality refuses to conform to expectation, when the cosmos reveals itself to be stranger and more urgent than theory allows, knowledge deepens. The mystery of galaxy formation stands among the greatest of these shocks. A reminder that the universe is not bound by human timetables, nor confined to equations yet written. It unfolds in ways that remain beyond imagination, yet patiently invites discovery. And so, every time astronomers peer deeper into space, they are not merely cataloging stars. They are confronting the paradox of existence itself, that galaxies, by all rights, should not be there, and yet they are. Born too soon, too vast, too luminous for the rules we know, they shine as both evidence and enigma. They are the shock written across the heavens, the revelation that the universe is not only larger than once believed, but stranger, faster, and more restless than even its discoverers dared to dream. In the vast silence of the universe, human eyes are blind. The night sky, though adorned with scattered stars, conceals more than it reveals. For most of history, the cosmos lay hidden behind a veil of darkness, its secrets locked in distances that dwarfed imagination. To lift that veil, humanity began forging instruments of vision, machines designed not merely to look, but to pierce time itself. The first among them to change our cosmic story was the Hubble Space Telescope. Launched in 1990, it was not just a mirror set adrift above Earth, it was a revelation. Freed from the distortion of atmosphere, Hubble became a window without blur, a lens that opened onto the grandeur of the universe. With each orbit, it sent back portraits of galaxies spiraling like frozen whirlpools, of nebulae blooming in luminous colors, and of distant stars dying in cataclysmic bursts of fire. But its greatest triumph came from looking into the smallest possible fragment of emptiness. Astronomers aimed Hubble at a patch of sky no larger than the tip of a needle held at arm's length, a place seemingly devoid of stars. After days of exposure, darkness gave way. Out of the void emerged thousands of galaxies, each containing billions of suns. The Hubble Deep Field became a testament that even the barest corner of the heavens overflowed with worlds. The universe was not empty, but saturated with creation. Yet Hubble's vision, though vast, was bound to visible and ultraviolet light. The cosmos, however, speaks in many tongues. Beyond the spectrum familiar to the human eye lies a symphony of signals. To hear them, other instruments were needed. The Chandra X-ray Observatory opened a window onto violence. Its sensors captured the universe at its hottest and most extreme. The searing glow of supernova remnants, the blazing accretion disks spiraling into black holes, the jets of matter launched at near-light speed from quasars billions of light-years away. Where Hubble revealed beauty, Chandra revealed power. In its images, the cosmos appeared not as a quiet expanse, but as a battlefield of energy, where gravity and light collided in ceaseless struggle. Then came the Spitzer Space Telescope, tuned to the deep infrared. Where visible light could be blocked by dust, infrared slipped through. Spitzer unveiled hidden nurseries where stars were born, still swaddled in clouds of gas. It revealed galaxies shrouded in veils invisible to Hubble's eye. It showed the glow of worlds around other stars, offering the first steps towards sensing the atmospheres of distant exoplanets. On the high desert plateau of Chile, another eye opened, not in orbit but anchored to the Earth. The Atacama Large Millimeter/Submillimeter Array, known as ALMA, stretched across the barren landscape like an orchestra of silver instruments, tuned to wavelengths between radio and infrared. ALMA traced the faint whispers of cold gas, mapping the raw material from which galaxies, stars, and planets arise. It could see the filigree of cosmic structure etched in the afterglow of the Big Bang, and the swirling disks around young stars where planets assembled grain by grain. Each of these instruments became an extension of the human eye, expanding the spectrum of vision beyond biology, beyond atmosphere, beyond Earth itself. But even together, they were fragments of a greater whole, incomplete glimpses of a vast and ancient story. In 2021, a new eye opened, carrying with it the weight of generations. The James Webb Space Telescope, a golden honeycomb of mirrors, unfolding like an origami flower a million miles from Earth. Where Hubble was a telescope, Webb was an arc of ambition, carrying within it the promise to reach farther back in time than humanity had ever dared to dream. Its mirror, 7 times the collecting area of Hubble's, was built to gather the faintest embers of the first stars. Its instruments were cooled nearly to absolute zero, so that the warmth of the telescope itself would not drown the ancient light it sought. With Webb, astronomers turned their gaze to an epoch less than 500 million years after the Big Bang, a dawn long hidden beyond reach. The first images stunned the world. Galaxies appeared not as distant smudges, but as luminous swirls, compact and blazing, born in a universe scarcely awakened. These were among the earliest structures, fragile islands of light in a vast cosmic sea still dark with primordial hydrogen. To look upon them was to trespass into time. Each photon Webb captured had traveled across the abyss for more than 13 billion years. Every galaxy was both there and then, a fossilized moment from the infancy of everything. To gaze upon these ancient sparks was to witness the universe remembering itself. The feeling was not triumph, but humility. In the colors of Webb's images, humanity glimpsed the boundary between nothing and becoming, the line where silence erupted into song. These galaxies, smaller and more chaotic than the majestic spirals of today, were the universe's first breath, the raw syllables from which cosmic history would be written. And yet, even in that first glimpse, questions multiplied. How could such galaxies exist so soon? Were the first stars larger, hotter, stranger than theory had foretold? Did black holes form earlier than imagined, igniting quasars in the universe's youth? Webb's revelations unsettled certainty, reminding science that each answer expands the horizon of mystery. The instruments of vision are not mere machines. They are bridges across time, carrying human sight beyond the horizon of the present. Each one speaks a different dialect of the cosmos, and together they form a chorus. Hubble, with its shimmering galaxies, Chandra with its storms of X-rays, Spitzer with its veiled nurseries of stars, Alma with its maps of cold beginnings, Webb with its eyes on the dawn. Through them, the universe ceases to be an abstraction. It becomes intimate, luminous, alive. In a grain of sky, thousands of galaxies bloom. In the faintest light, the birth of time itself is revealed. And standing before these visions, humanity is confronted with the paradox of its own existence. Small enough to vanish in the immensity of space, yet capable of seeing across its vastness. The act of looking back is more than science. It is reflection. To peer into the cosmic dawn is to glimpse the fragility of beginnings, the frail sparks that became suns, the scattered atoms that became worlds, the faint galaxies that would, across billions of years, evolve into the stage for life and thought. Every image is not only a map of what was, but a mirror of what is. A universe that creates observers capable of remembering its birth. The story of the cosmos is told in light. And through these instruments, humanity learns to listen, patiently, reverently, to the faint echoes that have traveled since the beginning. In the silence of deep time, the James Webb Space Telescope gazed further than humanity had ever looked before. And there, in the faintest glimmers of ancient light, something impossible appeared. Galaxies, not fragile swirls of newborn stars, but vast, massive systems, already formed, already luminous, when the universe itself was still in its infancy. Astronomers had expected the Webb telescope to paint a picture of beginnings. Tiny, chaotic fragments of gas struggling to ignite the first starlight. Instead, Webb revealed fully realized galaxies, glowing with billions of stars, existing when the cosmos was less than 5% of its current age. It was as if one expected to find sparks, but instead discovered a roaring firestorm. In cosmology, time itself is measured in light. The farther we see, the younger the universe becomes. The Webb telescope, tuned to infrared wavelengths, can pierce through cosmic dust and stretch of expansion, unveiling scenes from just a few 100 million years after the Big Bang. And there, astonishingly, lay galaxies as massive as our Milky Way, born only 300 to 500 million years after creation. The contradiction struck at the very core of astrophysics. According to the Standard Model, galaxies require vast stretches of time to grow. Gas cools, stars ignite, gravity sculpts matter into shape. By the epoch Webb was observing, galaxies should have been fragile infants, dwarfs, irregular in form, still groping toward coherence. Yet the Webbs I saw grandeur. Heavy systems, structured and luminous, as though entire epochs of cosmic history had been skipped. It was as if evolution itself had raced forward in a sprint no one predicted. The finding rippled through the scientific world. Has Webb uncovered mistakes in our measurements? Were these truly massive galaxies, or illusions of brightness masquerading as bulk? Teams of astronomers ran simulations, recalibrated instruments, and checked the redshift, the cosmic fingerprint of distance and time. Again and again, the verdict held. The light came from deep antiquity. The impossible galaxies were real. This was not a small anomaly. It was a challenge to the foundation of the Lambda-CDM model, the reigning framework of cosmology built on cold dark matter and dark energy. According to this model, structures in the universe assemble slowly, like mountains rising from the sea. But Webb's vision suggested something else. Colossal structures arriving far too soon. If true, it meant that our understanding of how matter clumps, how stars ignite, how galaxies evolve was incomplete. Perhaps gravitation behaves differently under extreme conditions. Perhaps the properties of dark matter, still unknown, still unseen, are not what we imagined. Or perhaps the story of cosmic time itself is written in a language we have yet to learn. One galaxy in particular, labeled CRS 93316, emerged from Webb's early release surveys. Its light dated back to just 235 million years after the Big Bang. In cosmic terms, it was as though the universe had only just opened its eyes. Yet already, this galaxy burned with the light of a billion suns. For astronomers, the paradox deepened. How could so much matter have collapsed so quickly, when even hydrogen, the simplest element, was only beginning to settle into stars? Another candidate, Glass Z13, glowed at a redshift of 13.1, its photons traveling across 33 billion light-years of expanding space. According to models, galaxies this large should not exist until at least 1 billion years later. And yet, there it was etched into Webb's vision, undeniable. These were not lone anomalies, but part of a growing pattern. The deeper Webb peered, the more such giants appeared, each one a cosmic riddle, each one a fracture in the timeline we thought we understood. What could explain such impossible maturity in the cosmic dawn? Several possibilities emerged, each as mysterious as the galaxies themselves. One hypothesis suggested that stars in the early universe formed with astonishing efficiency. Instead of the slow burn we observe today, primordial gas might have collapsed with furious speed, igniting vast populations of stars in mere tens of millions of years. Another proposed that dark matter, the unseen scaffolding of the universe, clumped far more effectively than predicted, dragging gas into dense knots where galaxies could form with unnatural haste. Others turned to more radical ideas. Perhaps our equations of gravity falter under such extreme conditions. Perhaps cosmic inflation, the mysterious burst that expanded the universe at unimaginable speed, left behind structures more intricate than we can yet model. And some whispered of even deeper possibilities, that our measurement of time, expansion, and light itself may hold unknown errors, that our window to the past is shaped by assumptions not yet tested. Science thrives in the tension between what is known and what is revealed. The Webb telescope was designed to answer questions, but in doing so, it has birthed new mysteries. The impossible galaxies remind us that the universe is not obligated to obey human expectations. The cosmos unfolds on its own terms, not ours. Each photon that arrives in Webb's mirror carries both knowledge and doubt, both evidence and challenge. For astronomers, this is not defeat but invitation. A call to revisit the equations of cosmic dawn, to test the foundations of Lambda CDM, to explore whether the universe may yet be stranger than we imagined. The impossible galaxies are not mistakes in the data. They are milestones on the frontier of ignorance. The sight of galaxies so impossibly mature in the youth of time touches something deeper than calculation. It stirs a question as old as astronomy itself. How much of the universe do we truly understand? The Webb telescope does not merely collect light. It confronts us with the scale of our unknowing. In its images, we glimpse a cosmos that resists simplicity, that carries secrets older than the stars we see. And perhaps in those ancient giants there is a lesson about ourselves. That knowledge is never final, that even the most elegant models may falter against reality, and that the greatest mysteries are often revealed not when we look forward, but when we look back into the beginning. The universe is still speaking, and through Webb's golden eye, we are only beginning to listen. In the darkness of the cosmos, galaxies appear as grand islands of light, spiraling, colliding, and reshaping over billions of years. But behind their brilliance lies an invisible hand, a set of forces that sculpt their forms, regulate their growth, and guide their destinies. At the heart of this unseen architecture is dark matter, a substance that cannot be touched, cannot be seen, yet outweighs all the stars, planets, and dust combined. Astronomers describe it as the invisible scaffolding of the universe. Where dark matter gathers, gravity deepens like a well, and into these wells ordinary matter, gas and dust, falls. This collapse marks the birth of a galaxy. Without dark matter halos, the cosmic fabric would be scattered with only diffuse clouds, never drawn tightly enough to ignite stars. Gas, once caught, begins a long descent. Pulled inward, it compresses, cooling as it falls, until the densities rise high enough for nuclear furnaces to ignite. Stars flare into existence, illuminating their dark hosts. But the birth of light is never peaceful. Each new star is a time bomb. The most massive among them live fast, burn hot, and end their lives in explosions so violent they reshape their entire neighborhood. Supernovae, with shockwaves rippling through the interstellar medium, regulate the pace of galactic growth. Too many, and the fragile gas is blasted away, starving a galaxy of its fuel. Too few, and matter collapses unchecked, smothering the galaxy in chaotic clumps. Feedback is the quiet law, balancing destruction and creation, chaos and order. Yet there is another, far deeper force at play, a paradox that sits at the very center of nearly every galaxy: the supermassive black hole. Once thought to be mere cosmic parasites, devouring everything in reach, they are now understood as engines of cosmic harmony. Their gravity anchors galaxies, while their violent outbursts of energy, jets stretching across hundreds of thousands of light-years, act as regulators, preventing galaxies from collapsing under their own abundance. A single black hole, smaller than the solar system, can decide the fate of a galaxy hundreds of thousands of light-years wide. This paradox, that the most destructive objects in the universe can also create order, is among the deepest mysteries of modern cosmology. Their feedback sculpts galaxies into their familiar shapes. Spiral galaxies, with arms stretched like cosmic whirlpools, emerge when angular momentum, gravity, and star formations strike a delicate balance. Elliptical galaxies, round and featureless, are the aftermath of ancient collisions, where ordered spirals were torn apart by violent mergers, their structures scrambled into luminous ellipses. Every galaxy, from the graceful spirals like the Milky Way to the great giant ellipticals at the cores of clusters, is a story written by these forces: dark matter scaffolds, collapsing gas, stellar feedback, and the paradoxical guidance of black holes. It is here, in this quiet struggle between chaos and order, that the true artistry of the cosmos is revealed. For galaxies are not merely collections of stars. They are living systems, shaped by invisible hands, and destined to evolve for as long as the universe endures. In the earliest instances after the Big Bang, the universe was not the grand stage of stars and galaxies we know today. It was a silence of fire, an ocean of pure energy, uniform to an almost unimaginable degree. Yet within this seeming perfection lay the hidden blueprint of everything to come. The theory of cosmic inflation suggests that in less than a fraction of a second, between 10⁻3610⁻3610⁻36 and 10⁻3210⁻3210 to 32 seconds after the birth of time itself, the universe underwent an exponential surge. Space itself ballooned faster than the speed of light, not by breaking Einstein's laws, but by stretching the very fabric in which those laws are written. What was once subatomic in scale became vast beyond measure. This expansion did more than stretch the cosmos. It smoothed its surface, erasing primordial irregularities, and leaving behind a nearly uniform canvas. Yet inflation also seeded the first hints of imperfection. Tiny quantum fluctuations, normally confined to the subatomic world, were caught in the surge and magnified to cosmic proportions. They became faint ripples in the newborn universe, variations in density so subtle they could barely be measured. Billions of years later, these ripples would blossom into galaxies, stars, and the scaffolding of the cosmic web. What we see today in the delicate patterns of the cosmic microwave background radiation, the afterglow of the Big Bang, are the fossilized imprints of those first whispers of quantum randomness. In this way, inflation did not merely expand the universe. It wrote its destiny. Out of nowhere, it carved the architecture of everything. The very act of existence. Galaxies spiraling, clusters colliding, stars forging heavy elements, traces back to those infant fluctuations, frozen into the fabric of spacetime. Inflationary theory remains one of the most powerful ideas in modern cosmology. It explains the universe's smoothness, its vastness, and the strange consistency we observe across distances billions of light-years apart. And yet, the full nature of inflation, what drove it, how it ended, and whether it might still echo in hidden corners of reality, remains unknown. It leaves us with a haunting reflection, that all of cosmic history, all of life, may be the flowering of a quantum tremor, magnified by the breath of inflation into the grand symphony we call the universe. In the great silence of the cosmos, the human mind does not rest. Even as galaxies drift millions of light-years apart, even as the faint glow of the first stars flickers at the edge of detectability, humanity builds machines of glass and metal to chase them. The universe is vast, indifferent, unyielding, yet it leaves clues. And across laboratories, observatories, and supercomputers, scientists pursue those traces with quiet persistence, hoping to unlock the secrets of cosmic origin. In the cold vacuum beyond Earth, a golden mirror now peers into the abyss. The James Webb Space Telescope, a fragile lattice of beryllium and gold, was unfolded in the quiet solitude of Lagrange Point 2, a million miles from home. Its segmented eye drinks in ancient photons, stretched into the infrared by the relentless pull of cosmic expansion. Through Webb, astronomers now glimpse galaxies as they were just a few 100 million years after the Big Bang. Red smudges of light that mark the dawn of structure. Some appear startlingly mature, vast disks of stars assembled too soon, challenging existing theories of galaxy growth. Others are chaotic knots of gas, collapsing under gravity's hand, caught in the act of becoming. With every image, Webb whispers both wonder and contradiction. It confirms the richness of cosmic infancy, but also unsettles, hinting that our models of the early universe may be incomplete. And Webb is not alone. Far across the Atlantic, the Euclid Space Telescope, launched by the European Space Agency, turns its gaze toward a different mystery. Its mission, to map the dark geometry of the universe. Euclid charts how galaxies are arranged in the cosmic web, measuring the subtle distortions in their light caused by the hidden gravity of dark matter. Through billions of galaxies, it hopes to trace the invisible scaffolding that shapes the universe, and perhaps glimpse the fingerprints of dark energy, the enigmatic force stretching space itself. Soon, another eye will join them, the Nancy Grace Roman Space Telescope. With a field of view 100 times greater than Hubble's, Roman will watch entire swaths of sky at once, conducting cosmic censuses. It will search for the faint microlensing of stars caused by rogue planets and hunt for the ripples of dark energy across time. Together, these observatories form a trinity of vision, each designed to peel away a different veil, each probing a different aspect of the unknown. Yet telescopes are not the only instruments of cosmic pursuit. In the dim hum of supercomputing centers, galaxies are also born inside machines. Projects such as Illustris, Eagle, and the Millennium Simulation attempt to recreate the entire sweep of cosmic history, not through lenses and mirrors, but through equations and code. They begin with a primordial soup of particles, their motions governed by the laws of gravity, fluid dynamics, and thermodynamics. Supercomputers push these equations forward in time, watching as fluctuations in density grow into filaments, filaments into clusters, and clusters into galaxies. The results are astonishing. Out of mathematics alone, structures emerge that echo the cosmic web observed by telescopes. Spiral arms unfurl. Star clusters condense. Jets of plasma burst from simulated black holes. These digital universes allow scientists to test hypotheses, tuning parameters of dark matter, star formation, and feedback to see what kind of cosmos results. Yet, no simulation is perfect. The early galaxies observed by Webb appear to form faster and larger than even the best models predict. This dissonance suggests that either unknown physics guides their birth, or our current approximations fall short of nature's complexity. Still, in their errors, simulations become teachers, showing not only what we understand, but also where mystery still reigns. While telescopes and simulations map the grand architecture of the universe, others pursue the ghostly substance that underlies it, dark matter. In caverns beneath mountains, far from the noise of cosmic rays, physicists build experiments of exquisite sensitivity. Deep within Italy's Gran Sasso, in South Dakota's Sanford Underground Lab, and in China's Jinping Mountains, vast tanks of liquid xenon and argon wait in silence. Their hope, that a passing dark matter particle, perhaps a WIMP, a weakly interacting massive particle, will collide with an atom, releasing a faint flash of light. So far, the silence has held. Each new generation of detectors pushes deeper into the void, constraining the mass and interaction strength dark matter could possess. Meanwhile, particle accelerators like CERN's Large Hadron Collider smash protons at near light speed, hunting for exotic byproducts that might hint at hidden particles. Some theories propose axions, lightweight particles born from quantum symmetries, that could permeate the cosmos. Others suggest dark matter may not be particles at all, but rather an emergent property of spacetime, requiring modifications to the very law of gravity. The absence of detection is not failure, it is guidance. Every null result narrows the landscape of possibility, sharpening the questions left to ask. But perhaps the most delicate pursuit of all is the quest to see galaxies in the very moment of their assembly. Not merely ancient galaxies long formed, but the act of formation itself, the condensation of gas, the ignition of first stars, the awakening of black holes. Future missions like the Roman Telescope, the Square Kilometre Array, and perhaps one day LUVOIR or HABEX dream of catching this moment. By peering at the faint radio whispers of hydrogen, the most abundant element, astronomers seek to map the era of reionization, when the first stars bathed the cosmos in light. Already, Webb has offered hints, galaxies appearing too massive too soon, as if the cosmos itself hurried in its infancy. Are these anomalies artifacts of measurement, or signs that cosmic dawn unfolded differently than theory predicts? If such galaxies are truly as large as they appear, it may suggest that star formation began earlier, more efficiently, or under different rules than expected. Perhaps unseen processes, dark matter physics, exotic cooling channels, or primordial black holes accelerated the cosmic clock. Science advances not only with answers, but with questions sharpened by new tools. The ongoing pursuits of telescopes, simulations, and experiments are not isolated endeavors. They are threads of the same tapestry. Each seeks to connect the faint glow of the first stars, the vast lattice of galaxies, and the unseen mass that binds them. And yet, beneath the equations and detectors, lies a philosophical weight. To search for the universe's first galaxies is, in a sense, to search for the conditions that allowed everything else, including us, to exist. To seek dark matter is to admit that the visible world is only a fraction of reality, that the cosmos hides its true substance behind a veil. To simulate universes in silicon is to grapple with the thought that perhaps ours is just one of many possible realities, shaped by laws that may be universal or perhaps arbitrary. These pursuits are not the end of mystery, but its deepening. For every discovery, new horizons emerge. The telescopes will send back more light. The detectors will listen longer. The simulations will grow finer. And still the universe will remain vast, ancient, and elusive, always one step beyond complete understanding. The story of cosmic origins is not finished. It is only the beginning. There is a boundary that no telescope can cross, a veil woven not by dust or distance, but by the very laws of physics. Beyond it lies a silence so profound that even light itself cannot speak. This boundary is called recombination, a moment nearly 380,000 years after the Big Bang, when the universe cooled enough for the first atoms to form. Before then, photons scattered endlessly off free electrons, trapped in a stormy sea of plasma. The cosmos was opaque, like a fog too dense to see through. Only when the fog cleared did light finally break free, rushing outward across the ages to paint what we now call the cosmic microwave background, the faint afterglow of creation itself. That glow is the oldest light we will ever see. No matter how powerful our telescopes, no matter how far our gaze, we cannot look beyond it. It is the ultimate horizon, a cosmic curtain drawn over the universe's most secret birth. And yet, science is never still. If eyes cannot pass the horizon, then minds must. Through mathematics, through simulations, through echoes hidden in the structure of galaxies, astronomers have learned to reconstruct what the veil conceals. Like shadows cast upon a wall, the present universe carries the fingerprints of its earliest moments. Every cluster of galaxies, every arc of starlight, every distortion in the fabric of spacetime is a remnant of a drama that unfolded long before light itself could tell the tale. This is the paradox of cosmic birth. We may never see the first stars ignite, the first galaxies assemble, but we can trace their outlines, like archaeologists dusting the shape of bones from the earth. The James Webb Space Telescope has already carried us closer than ever before to that hidden dawn. In its deep fields, we glimpse galaxies so young they appear as fragile sparks, formed when the universe was only a few 100 million years old. Their light, stretched thin by the expansion of space, arrives to us as whispers from the edge of time. Yet even Webb cannot pierce the absolute barrier. It can only approach, circling the edge of an ocean we may never step into. But there are other messengers, older than light, older even than recombination. Gravitational waves. Ripples in space-time, born from the motions of mass itself, do not scatter like photons. They can pass through the opaque plasma of the early universe unbroken, carrying with them a memory of events hidden beyond the horizon of light. If we could detect the faintest of these primordial tremors, we might glimpse the fingerprints of cosmic inflation, the violent surge of expansion that set all galaxies in motion. And so, vast detectors like LIGO, Virgo, and future observatories in space, such as LISA, wait with exquisite patience. They stretch their arms across continents and orbit to catch the faintest shiver in reality's fabric. For within those shivers may lie the only voice from before the first light. Even neutrinos, the ghost particles of the cosmos, offer clues. Produced in abundance during the universe's first seconds, they still stream through us today, unbound by the fog that once trapped light. Scientists dream of building instruments sensitive enough to hear this cosmic neutrino background, a silent chorus from a time when atoms themselves had not yet formed. In this way, though our eyes are blind to the true birth, our minds reconstruct its silhouette. With every model of cosmic evolution, every supercomputer simulation, astronomers breathe life into a scene they will never watch unfold. They conjure galaxies assembling, stars igniting, matter gathering under gravity's slow hand. The colors and shapes may be speculative, but the physics is real, anchored by the relics we can measure today. And perhaps this is where science meets poetry. For what does it mean to seek a moment forever hidden? To chase a birth no I will witness? It is like listening for a song carried by an instrument long broken, its melody echoing only in the spaces between notes, or like reaching for the shadow of a tree whose trunk has long since vanished. The act is not futile. On the contrary, it deepens the mystery, for in every galaxy above us, in every starlit night, we feel that hidden birth. We know it not as a sight, but as a presence woven into all that exists. Each spiral galaxy, with its rivers of stars, is not just an island of matter. It is a monument to the first flicker of order from chaos. Each black hole, each star cluster is a child of that dawn. When we look upon the Milky Way, we are not looking at a single object, but at an echo, a cathedral built from the stones of the first galaxies. Perhaps this is the essence of the cosmic paradox. We cannot witness the first light, yet without it nothing could be seen. We cannot watch the first galaxies rise, yet every galaxy bears their signature. We cannot stand at the moment of birth, and yet we stand in its aftermath, breathing its consequences with every second of existence. The horizon is not the end of knowledge. It is a mirror showing us that there are limits, and within those limits infinity still speaks. For the true wonder may not lie in the seeing, but in the knowing that something vast and unknowable preceded us, that we are its children, still searching for its face. So, will we ever witness a birth? Not with our eyes, not in the way we witness a sunrise or a flower's first bloom, but in the quiet symphony of particles, in the trembling of space-time, in the glow of galaxies, we already have. For every star above is proof that the dawn has come, and in their light, the universe whispers, the birth is not gone, it is everywhere. The search for the first galaxies is not only a quest for light lost in the depths of time. It is a search for meaning, for what lies at the heart of beginnings. Astronomers speak of cosmic dawn, that fragile moment when hydrogen, once shrouded in darkness, ignited into the first stars, and the first galaxies swirled into being. But behind this language of physics, hidden inside its equations, lies something deeply human, a longing to understand the story of existence itself. The cosmos does not hand over its secrets easily. Light from those ancient times travels to us across more than 13 billion years. It is stretched by expansion, dimmed by dust, scattered by intervening clouds. Yet still it arrives, delicate photons landing on the mirrors of telescopes, whispers from an age when galaxies were new. And so, the act of searching is itself a metaphor. To ask where galaxies came from is to ask where we came from. Spirals of stars form out of collapsing chaos, just as life itself seems to rise from disorder. In each glowing arc of starlight there is a pattern that mirrors our own emergence, fragile order born from violent beginnings. When we look at a spiral galaxy, we see not only a structure of gas, dust, and stars. We see a symbol of endurance. Its arms coil like the unfolding of time, wrapping chaos into symmetry. Astronomers measure the velocities of stars within these arms, test models of dark matter halos, and trace the flows of gas feeding new generations of suns. But even beyond this, the spiral suggests something larger. The universe has within it a tendency to sculpt beauty from turbulence, order out of chaos, light out of darkness, being out of nothingness. This is not an accident of poetry, it is the very architecture of the cosmos. Human birth and cosmic birth are bound together by this rhythm of emergence. A child comes into the world through a process both fragile and fierce, cells dividing, organs forming, consciousness flickering awake. So too do galaxies form. Gravity tugging, gas collapsing, stars igniting, black holes stirring in the center like dark hearts of inevitability. We often imagine ourselves apart from this process, but the truth is written in every atom we carry. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged inside the furnaces of stars. The very dust of galaxies became the dust of us. To speak of galaxy formation is to speak indirectly of human formation. The boundaries blur. Our story is their story, told on a smaller stage. Albert Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. He meant that it is astonishing that minds born from stardust can look back upon the stars and make sense of them. That mathematics, invented on Earth by fragile creatures, can describe the bending of space, the expansion of time, and the birth of galaxies. It is as though the universe has grown a way of looking back upon itself. Through us, the cosmos has gained a mirror. And in that mirror, galaxies do not remain distant abstractions. They become family, ancestors whose luminous lives gave rise to our own. Yet mystery remains. Even with the most powerful instruments, we may never see the very first light. The cosmic dawn hides behind a wall of darkness, the neutral hydrogen fog of the early universe. Some light is lost forever, absorbed before it could travel. Some questions will remain unanswered. But this does not make the search less meaningful. It makes it more profound. The act of searching binds us to the story. To turn telescopes toward the edge of time is to acknowledge that we belong to something larger than ourselves. A narrative written in light, gravity, and dust. Even if we never capture the very first photon, we are already participants. Every heartbeat is proof that galaxies succeeded in their work. Every breath is a reminder that stars lived and died long before us, seeding the cosmos with the elements of life. We are not merely observers of the cosmic story. We are its continuation. There is humility in this realization, and there is a kind of grace. The galaxies we study are not distant strangers. They are reflections, spirals of order rising from chaos, like the spiral of a seashell, the swirl of a hurricane, the whirl of a fingerprint. Nature repeats itself in patterns across scales vast and small. The birth of a galaxy and the birth of a child both speak to the same truth. Emergence is the universe's greatest art. Perhaps that is why the search feels so urgent. To understand beginnings is to understand ourselves. What we truly seek is not only the dawn of galaxies, but the dawn of meaning. And so the documentary of the universe closes, not with certainty, but with wonder. The galaxies that formed long ago still shine, their light brushing against the retinas of those who gaze up at night. Every photon is an ancient traveler. Every star is a reminder that beginnings, however hidden, always leave echoes. We may never stand at the threshold of the very first dawn, but we stand within its legacy, beings born of starlight, daring to ask how it all began. The universe is not obliged to answer, but still it whispers, and we, fragile listeners in a sea of silence, are part of that whisper. For as long as galaxies turn, as long as stars ignite, as long as life wonders about its origin, the story continues. And so does the search.